Okay. Okay, I'm going to start with presenting my group at our university. Pontificia Universidad Católica de Chile is a university in Chile, in Santiago. We are a very, very small fire group. It's just me and 5 other people. So, and we've got 2 major research line within fire safety. So one of them is timber fire safety, where we do a lot of modeling. And this is where I got my PhD student, Ignacio Calderón. I've got a postdoc, which perhaps many of you know from name at least, which is Agustin. And I have a master student starting, well, just started last semester, Ignacio, and we are trying to do as well some experimental work and combine that with numerical simulations. So that's very standard. And then I have this new project with fire safety of lithium-ion batteries in underground mining, where I have now a postdoc, which again, many of you might know from name, Carlos Walker-Avena, who started with me half a year ago. And I've got a new PhD student who just started from Pakistan, Zulfikar Ahmed, who is basically now in the first stage of his PhD, so not really contributing yet. So as you see, fire safety in Chile is, in lithium-ion batteries in Chile is just me and Carlos, basically. So that's just a bit of context. This is just very quickly to show you a few. This is our campus, our university, which is simple. I always present this, and in other parts of the world, they all get very, oh, this is awesome. But at UQ, you have your own very nice campus, so it's not that spectacular compared to that. But anyways, this is our campus. I just want to make a very quick comment about this building here. You see, this building received, I can't remember the name of the prize, but this is like the Nobel Prize for Architecture a few years ago. I have serious concerns about fire safety in this building because it's a wooden core, like a timber core, well, timber covered core, and then glass around that. It's basically a chimney, a big, huge chimney. Anyways, this is just about the place where we are working. Now to the subject. A bit of context. Chile is, in certain ways of looking at it, is a world champion in going renewable. Around 70% of our electricity is generated from renewables. Depends a bit on the year and the month, but it's in average it's about 70%. Practically all new projects in energy generation are renewables. There's no more thermoelectric generation planned. And we have a massive solar energy potential. There's the highest solar irradiation in the north of Chile, in the Atacama Desert, with about 3,800 kilowatt hour per meter squared, which is very, very much. And there's a potential for photovoltaic electricity or generation of over 1,800 gigawatts. So there's lots to do. And there's a big push from government, from industry as well, and from the rest of the world to go renewable, and we are basically doing that. Since we have that big potential, we can actually, in theory, we could export energy at this point. We have more energy potentially available, than we could use. So we could export, which is something that the Chilean government has tried to plan for in the long term. Chile wants to replace copper, which is our current kind of salary, we say, with energy. That's what we want to export in the future. Rather than copper, export energy. So for that, we need to somehow come up with a way of storing this energy and sending it somewhere else. There's alternatives, batteries, obviously. There's hydrogen, ammonia. All these things are being discussed. There's lots of planning from government, so this is good. Chile is trying to go step ahead, but it's all very much of the future. We can't do this now, but it's just a little bit of context of why Chile is so, why lithium batteries are so such a big thing in Chile. And here I go to the detail of how this connects to mining. Chile, we as I said before, we call copper our salary because it basically pays for everything we do. The mining sector contributes, what is it, 14% of to the GDP, and 58% of total exports. Is a lot. So all the economy is based on exporting copper, basically. 10% of the Chilean workforce is directly or indirectly employed by the mining industry. That's a lot. So mining is very, very important to us. Within mining, there's Codelco. Codelco is the Chilean state-owned mining company. It's arguably the world's largest copper producer. It depends a bit on the year. Again, there's some other, but normally it's the biggest copper producer in the world. It produced 1,300 million metric tons of copper in 2024, which again is a lot. And they operate the largest underground copper mine in the world, which is El Teniente, with more than 4,000 kilometers of tunnels. Well, this is to show you how much we produce, but at a cost. In 2023, Codelco emitted approximately 9.8 million tons of CO2 equivalent, which is about 10% of what the country emits. So it's a massive fraction of what we emit in greenhouse gas emissions is done by Codelco. So to mitigate that, Codelco committed to electrifying its entire underground operation by 2030. So they did this 3 or 4 years ago. So they had 7 years to go 100% electric in underground mining. There's not a single one electric vehicle in mining now. Well, now there are a few. A year ago, there was not a single one. And they had 7 years to go electric. They did a lot of analysis about this, but all of it based on, is it possible how far can the trucks and the LHDs and all these the machinery, how far can they go into the mine? Is it possible to have all this? Like, do we have to have underground charging stations? Can it be outside? All this was planned before they committed. What they didn't think or what they didn't consider when they committed to this was that lithium-ion batteries can burn. They hadn't considered that. Which was obviously is a bit of a problem because you don't want to have batteries burning, and you surely don't want to have batteries burning within a mine, because a fire in a mine is the worst thing that can happen at all. So there was a big incident, well, the big accident, 1942 or something in Chile, where 100 miners were killed in a tunnel fire, and it's something that still is within Codelco's culture, is very present. Everybody talks about that. So this big accident, so that cannot happen again ever. So we need to make sure that there is no fire or no big fire in mining tunnels, and that's the problem that we have now. The diesel engines, as they are used now in mining, are understood very well. So they know what the risk is, they know what the hazard is, and they know how to mitigate the consequences. But we don't really know that in the case of electric vehicles. So this is just an example of one of the machines or the vehicles that they just bought, I think. So this thing here in the back, that's the battery. So it's massive. It's a massive battery, and they don't charge the batteries on the vehicle. They exchange the battery. So the vehicle goes into a place where they have all these battery chargers, and just replace them with a new one and goes out again. So there is a movement of batteries on the vehicle and from the vehicle to other places. So why is it? I don't have to talk about this in detail. This obviously is a problem because these lithium-ion batteries can go into thermal runaway under certain conditions of abuse, mechanical abuse, thermal abuse, or electrical abuse. Obviously, within a mine, I don't know if you've ever been in a mine or seen how rocks fall off the ceiling, or there is a big probability or likelihood of mechanical abuse in mines. So this is something that we cannot really rule out. We don't really we can't make sure that there will never be an incident of a battery within a mine. Obviously, when this happens, from runaway, the temperatures rise, which makes the increases the chemical reactions, the heat release, and the heat can't be dissipated. So that makes this loop of feedback loop that makes the whole thing to basically explode at some point and produce massive amount of heat. Obviously, as batteries grow, this is something that actually I haven't seen that is talked very much about it, but from a very just theoretical point of view, if you have a battery that generates proportional to the volume, right, and dissipates energy proportional to the surface area, as these batteries grow, as they become bigger, they tend to get hotter and tend to go into thermal runaway more, or to be more prone to going to thermal runaway as they grow. This is something I haven't actually seen in literature that people talking about that. So I'm not sure why this doesn't seem to be a problem. I guess it's because big batteries they all have thermal management systems, so they are actively cooled, so they won't go into thermal runaway. But if it's actively cooled, that's something that can fail, and we have to make sure that that doesn't happen. As I said, so underground mining, this is a fact. They will adopt high capacity, very large lithium-ion batteries. There is an increased likelihood of mechanical abuse in mines compared to outside. And obviously, we have to consider the risk of using lithium-ion batteries in this environment. And the risk is obviously the multiplication of probability of occurrence times the severity of the consequences. We can't really rule out of this happening, so the probability will be at some point different from zero. So we have to make sure that the severity of the consequences is limited, and so that the risk is acceptable. The challenge now is that we don't really understand lithium-ion battery fueled vehicles as well as we do diesel fueled vehicles. So we don't really know how P and S, our probability and severity, how they interact. And all the protocols that exist, and they're very strict in mining, may not apply for this new risk. So there is need for a quantitative risk assessment to be able to say with numbers what the risk is and how we can mitigate it. How do we do that? How do you do quantitative risk assessment if you have a mine, if you have vehicles with massive batteries? You can't just go into the mine and burn them and see what happens. We saw the tests with small battery cells yesterday in the lab. That makes a lot of noise and makes a lot of release a lot of energy. If these batteries become very, very big, then the outcome might be complicated and very, very hard to manage. So we need to find an alternative to massive testing at real scale. So how do we do this? So this is the point where Codelco, the mining company, said we need help to manage this, and they approached us and asked us to help them look into this problem and find new ways of reviewing the protocols on one hand. So there's part of this, what we're doing is going through the regulations and protocols, and there's, on the other hand, there's a need of scientific research to really understand what the problem is and how we can mitigate the consequences of these things failing. They funded 1 year of research, which is now finishing. And this is what I said at the beginning. Before this happened, they approached us a year ago. when they approached it, I didn't really have any expertise or any experience with lithium-ion battery fires. So we basically started learning about this, started studying it, and now we've been doing some simulations, some modeling of the consequences, but it's still a very, very early stage work. We basically use this year to kind of get an expertise, an understanding of the problem, to convince them to fund 3 more years. And that's what we now doing is to propose a new project, a new stage of the project, to take this to the next level and start doing more interesting things. So first thing we did when we had to look into that was to do a literature review, to try to be as complete in that sense as possible. And we had we looked at what is it we actually do know about lithium-ion batteries fire safety. And what we found is that there is a lot of work being done on thermal runaway. And I'd say there's papers coming out by the day on thermal runaway, almost exclusively on small cells. All the research, all the scientific investigation is being done on 1 cell, 2 cell, maybe 5 cells. I've seen some modules as well, but it's all small, very, very small scale. And there's almost no research. I didn't find any on the scaling of the hazard with size. So what happens if big batteries go into thermal runaway? How do they behave? How do they interact with the environment? We don't know. I didn't find any. There's 2 or 3 studies of electric vehicles, road vehicles being burned, but other than heat release rate or temperatures at some point weren't measured and not very to the detail. There's no structured research on large scale batteries. And this is the other thing that we found, and which is, in my view, a bit worrying, is that there's a major divergence between scientific research on one hand and industrial applications. These vehicles exist, they're being used, massive batteries, but all the scientists, they're still not playing, they're still working with cells, right? And so where is this middle ground? Do the people from industry know that? Do they care? Do the researchers know that? Obviously no, but how do we communicate? How do we make sure that this is not a problem in the short term? And so yeah, what we need to find out is how do large lithium-ion batteries burn in a confined environment? Because that's a different story. We've got big batteries burning, and we've got them burning inside a mine, which is a very narrow tunnel compared to the size of the vehicles. So we have to actually look at the burning of big batteries, of big packs of batteries in a confined environment. And on the other hand, what do we know about fire safety in underground mines? Again, there is a lot of research in the past and being done on tunnel fire safety, but it's almost exclusively on road tunnels. Mining tunnels are very, very different from road tunnels. Mining tunnels don't have an entry and exit. They are networks of tunnels, and very, very long. El Teniente is 4,000 kilometers of tunnel networks. They're all connected. There's different levels. So there's very, very little on fire safety research in mining tunnels. So, for example, modeling tools. There's, again, lots of work being done on CFD modeling in tunnels, but not so much on CFD modeling in network tunnels, in tunnel networks, sorry. So again, we identified 2 big knowledge gaps, and we thought, well, to identify or to calculate the risk of using lithium-ion batteries in mining, as I said before, I can't do hundreds and hundreds of real scale tests. We need to have some kind of model, some tool that permits us to evaluate, to assess risk based on simulations. So there's a need for simulation tools that can provide relatively cheap evaluation of the severity of different lib fires, fire scenarios. We, at the end of this literature review, we identified, as I said, these things are switched. So I'm going to just mention the two research questions, which we think are largely independent, which I think is a good, well, it's a good way to start, having two independent things which at some point have to be brought together, but we can start independently on them. How do lib fires scale with size, and how is the heat release rate affected by the enclosed environment? So how do big batteries behave in this underground mining environment? This is the one question, and the other question is, how does smoke propagate in tunnel networks, and how does tunnel characteristics influence smoke movement? Obviously, the second part has nothing to do with batteries, as it's put here. But at some point, we have to replace or give it information, the model, which comes from the battery. So at some point, we have to again put the two ideas together and to find a solution. But for starters, we think we can divide this in two problems and have them look at them in parallel. Study lib fires, large-scale lib fires on one side, and study modeling of tunnel networks and smoke propagation in tunnel networks on the other kind of track. And just go back. So what do we simulate? What is it we're interested in to evaluate the risk, to assess the risk? We have a very complex problem. There's fires in tunnels and lib fires, and so it's getting more and more complicated. This is very complicated. We can't really do it from first principles. There's no way that, at least with current models and current computational capabilities, to model the interaction of the battery, the thermal runaway, and the heat feedback, because that would involve solving CFD simulation in a large space, thousands of kilometers of tunnel, with the detail of the battery. So we would have to do conjugated heat transfer, and all this together is something that we could at the moment could not do. So we would have to simplify this problem and, as I said, separate them into two problems. CFD models, and this is something that is being done in mining general. When they study the ventilation of mines, they use 1D models. So it's nodal models to simulate the ventilation. When you do have a fire in the tunnel, there's a need of having at least the near field resolved. So the approach that we actually found in the literature to approach this problem is to combine CFD models, high resolution CFD models, with nodal models for the rest of the mine network that would basically give the boundary conditions to the CFD model, and then so you can iterate to find a solution. This is something we're now implementing. As I said, we have been working on this for a year. So now, for now, we did some. I'm going to talk about this in a bit. The validation of the CFD modeling of tunnel networks, and now the next step is to combine that with a multi-scale, to combine it with nodal models to produce a multi-scale modeling tool that can manage to find solutions for fire incidents in a big tunnel network. Oops, sorry. As I mentioned this before, road tunnels obviously are very different from mining tunnels. They have one inlet, one outlet. This is much more complicated, much longer, many different levels. different spaces. The tunnels are not all the same. There's smaller tunnels, bigger tunnels. There's holes within tunnels or between tunnels. So this is a very, very different problem. And we actually need to first validate any modeling effort that we want to do to be able to actually do some predictions on this. There's not very much data on heat release rates generally for mining equipment or mining vehicles. No, I'm not talking about battery-driven mining vehicles. It's generally driven. Generally, heat release rate for mining equipment, there's almost no data. We found one paper that reported temperature measurements and heat release rate of mining fire test, which was conducted by Hansen and Ingersoll in 2013. I don't know if they conducted in that time or they wrote like 5 or 6 different papers on this experiment. So I don't know when exactly they run the experiments. But the fact is that there's very, very little information on how things burn, how mining equipment generally burns and how they burn within a mining environment. Hansen and Ingersoll, they actually proposed a formula to burn the vehicles bits by bit and then putting them all together. So they came up with this formulation of a total heat release rate based on the smaller heat release rate of the components of the vehicle, which for their data worked very well, but it's not clear if you can just extrapolate this to any other problem. Anyway, this is the heat release rate we use to validate our model then and to come up with modeling tools. So basically, we use FDS-defined dynamic simulator to simulate this scenario that was run by Hansen and Ingersoll. So they had two mining vehicles in a tunnel within a mine, and so we replicated that geometry. So here we get the first problems, if you will. Mining tunnels, if you look at the picture, are very, very, how do you say, rough or not smooth, not like road tunnels. Road tunnels normally are cladded with some kind of to make them nicer, I guess. Mining tunnels are not. People don't care. So they're just as they are, how do you say, built out of rock, basically. And how do you represent this in CFD simulation, for example? CFD, obviously, you need to approximate, so you don't have the detail of the geometry, which obviously will at some point affect the flow. So these are things that we have to over time look into and see if that actually makes a difference and how to tackle. So we use this geometry and they had some temperature measurements. They provide the heat release rate. So what we basically the idea was to compare temperature measurements away from the vehicle based on the heat release rate that was provided by Hansen and Ingersoll, and then basically compared that in our simulations. So this is the plot that we got. This again, it's very limited data. They had just 1 or 2 thermocouples away from the vehicles, and these are the only data points that they have. And so this is the only data point that we had available to compare to our simulations. So again, the validation, I don't know if it's very good, but it's what we could do. There is not more data to compare to. But it worked fairly well. We had a good acceptable comparison to data. And then we started playing around a bit with parameters to see how this behaves when you change the heat release rate. So the reported heat release rate is more or less between a medium and a fast fire, somewhere in the middle. So we started playing with these parameters and and looked at how the ventilation, the different ventilation velocities affected the smoke propagation within this tunnel. Again, the difference to this and the road tunnel is that we had several outlets and different geometries. So again, this is just some simulations where we did some parameterization of the conditions of the tunnel and start looking at the results. The interesting thing is, and I guess this is more or less normal in tunnels, is that the outlet, the time it takes to go to the outlet downstream is not affected by the velocity, by the flow velocity, by the ventilation velocity, whereas the upstream upwind propagation velocity is affected by the wind velocity. So this is something that we found, and again, this is just a very initial study that we're doing to try to validate this model. There's some insights that we got from the simulations. So the stratified layer collapses. The collapse depends on the fire growth rate, which makes a lot of sense, and the ventilation. Faster growth collapses earlier, higher ventilation delays collapse. Smoke propagation is asymmetric. Yeah, obviously you have more smoke going downstream than upstream. But we did not find, well, we had to, or we will have to come up with an idea to redefine the critical velocity for backlayering, because again, since this is not one directional tunnels, but it's a tunnel network, there will be, the concept of critical velocity is not as obvious as it is in a road tunnel. So how does this matter for lithium-ion battery fires? Obviously, the heat reset that we used was based on a traditional vehicle, a traditional mining vehicle, not a lithium battery powered vehicle, and the heat release rate might be is probably very, very different, and especially in how fast it grows. So we will have to look into the possibility of modeling this, of inputting that into a model, and how that actually affects the output. We found very high ventilation velocities to control the smoke propagation backwards, more than it's normally reported in road tunnels, because the heat release rate is very big compared to the size of the tunnel. So this is something that, again, if there's a battery in the vehicle, might be even bigger, at least at the beginning of the fire, because the heat release is much higher. The problem is, the problem is that there is, again, I've said this many times, but I repeat it because it's very, very important. There's not much data to compare. We need more data sets for full-scale heat release rate generally, and in particular of battery-powered mining vehicle, to compare this to our simulations and being able to actually validate our models. So for the next stage of the project, what we now are proposing to fund and finance for us is on two fronts. We keep doing numerical work. For that, we want to now use geometry from the El Teniente mine and study different fire scenarios and compare them to some insight they have. They have had some incidents, and they don't have data, but they have seen things, so we can qualitatively compare simulations with what they saw. Get this multi-scale model to work. It's still being prepared, where we combine CFD modeling in the near field of the fire with nodal network for the far field of the fire to model the entire mining network. one thing that we want to again look into. We haven't done it, but we thought that machine learning techniques might help us to, at some point at least, try to be able to run more simulations and having them in less time. But again, this is something that we haven't looked into, and we need to start combining with the other work. And always keep in mind that it's just the two of us for now. So one of the things I actually want to make, or one of the goals of this presentation is to perhaps, I don't know, if there's somebody who might consider helping us. We will need more people working on this with us in the short term. There will be funding, hopefully. So we can, we need more people to do all this. We also want to, and this is actually the more important part of this second stage of this project, is to do some experimental work, and we want to do some real medium scale. I say medium scale because it's not very, very big scale. Experiments of lithium-ion battery fires in a mining tunnel. I'm going to talk about this in a second. And we want to, or we are doing some small, or we are preparing some small-scale experiments of cell-to-cell fire spread within a mining tunnel. This is something that we are building at the moment. We haven't tried it. This is the experiment setup that is being built. So this is an existing wind tunnel where we can preheat the wind coming in, or the air coming in. And we're adding this pipe, a concrete pipe, to mimic the mining tunnels, where we then want to place a battery cell in the tunnel and having some kind of gas burner here to produce a heat flux and try to ignite the cell and see what happens. Again, I'm very open to ideas, to criticisms. So if anybody has any ideas of how this could be, or what we should do, or we shouldn't do, perhaps, this is the moment to let us know, because we are very open to change any things. Now it's being built, so it hasn't been built, so we can still adjust things. The real scale experiments that we're planning, we are contacted a mine in close to Santiago. This is about 40 kilometers from Santiago, which is a very old and very small, well, comparatively small copper mine that's still being explored, but they have several sections of the mine that are not being used at this moment. And so they are willing, and they're very keen on helping us to put their, or let us use their tunnels to burn something in there. And they also are willing to give us mining equipment to burn, because they've got loads of old stuff lying around. But obviously there's no battery powered mining equipment. But for the time being, we would be happy to do at least traditional equipment and burn that in real scale, and then see if we can perhaps burn a battery in there. This is all future. We're now trying to convince Bodega that this is something that's necessary to do, and that we need more experimental data, and that they give us the money to do some fun experiments here. But yeah, we need, this is just one kind of data point that we could produce. We need more help. Not only we, generally, there's a need of more experimental work for large lithium-ion battery fires. So there's obviously, for us, this is a question mark, because we need help. So anybody who's interested in this, we are open to talk and to exchange views and ideas. Then we might work, well, it's, we want to, in parallel to the modeling of the tunnel networks, we want to look into the multi-physics simulation of the battery and how they interact, how the jet flame interacts with the tunnel wall, how that radiates heat back and accelerates the thermal runaway. This is something that we would like to do, depending on how many people we manage to add to the group. This is something I'd like to, out of personal interest, to work on as well. I don't know if this is even possible, and this is so complicated. The physics going in the battery, the interaction with the air that surrounds it, and the enclosure of the mine. This is very, very complicated. I'm not sure you can actually do this, but I'd like to try and compare that with the experimental data if there is any experimental data. As I said at the beginning, there's not much to show for now because we haven't done so much. We have only been trying to understand the problem and trying to learn enough about it so we can propose the next stage of the project and then start doing stuff that actually makes a difference. There's a lot of things that we don't know about how especially big lithium-ion batteries behave in fire. There is, as I said at the beginning, there's a divergence between what we do in research, what is being done in research, and what the industry demands and does. They, as I said, they are selling and they're operating big batteries. These mining equipments, they exist, they are being sold. Well, they bought a few and they're gonna start operating them, even without having the final conclusions of the project. So they're willing to obviously with a lot of care, but they're starting to use these mining vehicles, and this divergence is a bit. I think it's a bit worrying that there's no obvious communications between industry and researchers, at least in terms of what I've seen. So we're going to have to simulate to understand this problem and to be able to evaluate different outcomes of different scenarios. And for that we need a reliable tool to be able to simulate it and get the output that can be used to assess the risk. There is a need for more data, full-scale data, experiments, of lithium-ion batteries in general, and of lithium-ion batteries that are being used in mines. And for me, I think this is the most important conclusions. I can't do this on my own. So we need to collaborate. We need ideas. I need whatever input that we can get. So that's it for now.
Thank you. Just going to use this mic. Thank you very much, Wolfram. We've got 4 questions in the chat, but if you have any other questions, please feel free to, and if you want to just
how do you see this line with mine? Whoa, that is a good. Oh, is that the first question? No.
From Lucy, yeah.
Yeah, that's a good question. Well, this is, I don't know if it's directly related to your question, but one of the things that Codelco thought they could do with batteries was to have less ventilation, because they thought since they wouldn't have to evacuate the diesel gases, then they wouldn't need as much ventilation. But it turns out that if they have an incident, they will need more ventilation than in the case of a diesel fire, because the heat rate is going to be bigger or faster at least. So the ventilation, that's something that we don't know yet, and I don't think the operators of the mines know. I think they thought this would be cheaper because they wouldn't have to install all this ventilation equipment, but it's not like that, because in case of incident they obviously need ventilation put in place.
This is from Jaime, and I believe this is the Jaime you probably.
Yeah, I have seen Vensim. Yes, yes. I mean, it's widely used to design ventilation mines. Yes, it is. I don't know if it's used for fire assessment. I've seen it for for simulations of ventilating mines. I know that's used for that. I don't know if it's used for or how it compares. There's not much literature on vent fire and how it compares to data. So yeah, I know it, but it's, again, the other problem is that you can't just use it as you can use FDS because it's not available. You have to buy it, and yeah. Just random thought. Not sure how to represent it on CFD models in modeling lib fires in mines, considering that cannot simulate the effect of blowing loose dust to rocks in mine. Oh yeah, there's so many things that that would have to be approximated in some way. I completely agree. Yes, but we don't really have that many alternatives to CFDs because we couldn't just do a massive amount of real scale tests in mines. That would be too expensive, too dangerous, and that's not really an option. So we need to somehow represent this with some kind of model, and CFD-based models are the closest to reality that we get. But yeah, there's many problems, and what you mentioned is just a few of them. Once I from Professor talking about of batteries to precisely reduce the risk of smoke propagation. Yeah, well, I talked to one of the big battery or mining vehicles. How do you say producers? Manufacturers. Yeah, and they said, and they have these big batteries, and they say that they're very well encapsulated because they know they're operating in a complicated environment. So they have like a steel enclosure to make sure there's no mechanical abuse. And obviously, it depends on where you put the batteries and in the mining vehicle, you could reduce the risk or the way the smoke, the consequence of smoke propagation. I've done some recently learned on tunnel fact relations and prediction models from the I would like to have I would very much like that. Jose, I'd be happy to talk to you. I'll leave my email there, and I think the easiest way is that you just email me. You highlight the lack of full-scale data, but there have already been several EV fighters in road tunnels and car parks. Where do you see the biggest gap for silicon experiments? Well, first of all, it's a different scale of battery. These are a bit bigger than normal cars, and I think there's the confinement the confinement in a tunnel may be similar, but in a car park is very different. But there are there are a few tests, but not that many, and I don't think it's enough to characterize the behavior of lithium-ion batteries of that scale, at least. Event-fire does not seem like a robust model. It's more about propagating the fire model. Yeah, maybe use event-fire as this 1D model to expand FDS. That might be a problem. Lex, you have been using FDS. How have you validated to your approach? How FDS? Whoa, yeah. That depends a bit. I don't know that paper. Well, I don't know which paper it is. Depends a bit on the version of FDS. Old versions of FDS are not very good for tunnels, but they have big issues with tunnels or with with the pressure and the mass accumulation in tunnels. But the newest version of FDS is supposed to work well. We didn't have any issues. It worked well. Again, the validation that we did was very limited because we just had very few data points. I'd be happy to try other models. I'm not limited to FDS in my opinion. I'd be happy to try alternatives. Also, full scale would be great if you can manage it, but take caution with scale modeling. Yeah, thank you. I'll have a look at the paper. Can you send me that later on? Good.
Yeah.
Yeah, there's my email.
Excellent. There. Yes. All right. Given it's ticked over 5 o'clock local time, I'd like to thank Wolfram very much for his presentation. Yeah, all the best with your research.
Inviting me.